Hello everyone and welcome back to another StudyMonster OCR Computer Science video. In this lesson we're going to be focusing on the CPU performance, a core topic of the OCR J277 Computer Science specification. So have you ever wondered why some computers feel lightning fast while others take ages just to load? Is it magic? Is it luck? Is it whether your PC has an RGB light? Spoiler, it's not the RGB lights, it's your CPU performance. And today we're breaking down the three characteristics that make or break your system's speed: clock speed, number of cores, and cache size. So by the end of this video, you're going to understand exactly how each one affects performance individually and combined, just like the OCR J277 spec requires. So let's dive in. Your CPU is the brain of the computer. It fetches, decodes, and executes instructions billions of times every second. But not all brains think at the same speed. And more importantly, as my wife keeps telling me, not all brains can think about multiple things at once. That's why understanding CPU performance characteristics is so important. So let's break them down one by one. Clock speed. It's the heartbeat of your CPU. It tells you how many instructions per second the CPU can attempt to execute. A common misconception is if the CPU has a clock speed of 1 GHz or 1 billion cycles per second, then this means it's doing 1 billion fetch, decode, execute cycles. This is not the case because the fetch, decode, execute cycle has multiple steps. It could take 4 cycles to complete a full fetch, decode, execute cycle. However, the faster the clock speed, the more instructions that can be completed per second. But there's a catch. Increasing clock speed also increases the heat that's produced, the power consumption. So you can't just crank your CPU up to 10 GHz without cooking it like a pizza. For your exam, it's common to get a question where you're given specs of two CPUs. If two CPUs are identical except for the clock speed, remember the one with the higher clock speed will complete instructions much more quicker. Now, on to number of cores. Imagine you're trying to cook dinner, do homework and text your friend all at the same time. One brain, impossible. 4 brains, easy. A core is an individual processing unit inside of the CPU. Modern CPUs often have 2, 4, 6, 8, 12 or even 16 cores. Each can perform its own fetch, decode, execute cycle. Having more cores though doesn't always make your PC faster. If the task is a single-threaded task, for example some older applications, it can only use 1 core. So a fast single core is better than 16 slower ones. So for an exam point of view, increasing the total number of cores improves performance when the software is written to take advantage of them cores, or when tasks can be executed in parallel, allowing multiple instructions to be processed at the same time. This is exactly what OCR expects. Finally, cache size. Cache is like the CPU's private ultra-fast stack cupboard of data. When the CPU needs instructions or data, it checks here first because cache is much faster than RAM. There are usually different levels. Now you don't need to know the levels for your GCSE Computer Science exams. Level 1 cache is the smallest but the quickest. Level 2 cache is a little bit larger but much slower than level 1 cache, and then level 3 cache is even larger and it's shared between the different cores. But all of the caches are much quicker than RAM. Because the CPU spends less time wanting to fetch instructions and data from much slower RAM, if the cache size increases, more data can be stored closer to the CPU, which means that there's fewer trips back to RAM to retrieve that information. So the bigger the cache, the faster the execution overall. So increasing cache size improves performance because more instructions and data can be accessed quickly, reducing the time the CPU spends waiting to fetch information or data from RAM, and that is perfect OCR language. Welcome to scenario A. So here we're looking at a CPU with fewer cores. but each core runs at a much higher clock speed. So what does that actually mean? Think of this as like having one or two incredibly fast workers. They work at blistering speed, tackling tasks really quickly, but there aren't many of them. In a world of computers, a high clock speed means each core can complete more instruction cycles per second. So tasks that rely on a single thread, one stream of instructions, will run extremely fast. This setup is perfect for everyday applications, web browsing, productivity software and older programs, and lots of modern day games rely heavily on one main game thread. So even modern games often depend on a single main loop that controls the gameplay, physics and logic. So even if the CPU only has a few cores, super fast cores can make the game feel smoother and more responsive, but there's always a but. This design isn't ideal for workloads that rely on lots of threads running at the same time, so tasks like video editing, 3D rendering, or running multiple virtual machines on your computer will want as many cores as possible, even if the cores aren't as fast. So here's a summary. The CPU with fewer cores but a higher clock speed is fantastic for speed-sensitive, single-threaded tasks. It gives you fast performance where each instruction matters, but it won't match a many-core CPU where heavy multitasking or big parallel workloads are needed. It's all about matching the right CPU to the right kind of task that's being performed. Right, welcome to scenario B. So here we're looking at a CPU that has lots of cores, but each one of them cores runs at a lower clock speed. So what does that actually mean? Well, imagine you're in a huge group project, and instead of having one super fast student doing all of the work, you've now got a whole team of students, but their work at a normal pace. This is exactly how many core CPUs work. With 8, 12 or even 16 cores, the CPU can break different tasks into multiple threads and spread them across those cores. This is brilliant for video rendering, 3D modeling, running virtual machines or heavy multitasking tasks. It's even great for servers that are performing many different things at once, and any software that is designed to run lots of jobs at once. These workloads love having many cores because the CPU can process lots of instructions in parallel. But here's the catch. Even with all of those cores, each one has a lower clock speed, meaning each individual core completes the instructions more slowly than a high clock speed core would. So if you run a task that isn't designed for multi-threading, something single-threaded, it can take advantage of all of those cores. It has to sit on one core only, which makes it slower compared to a CPU with fewer but faster cores. So to summarise, a CPU with many cores but a lower clock speed is amazing for workloads that can be split across those threads, across those cores, but it won't always outperform a high clock speed CPU for tasks that rely on a single core. This is why different CPUs are better for different types of work, and why simply counting how many cores a CPU has doesn't tell the full story. So remember, the software and the tasks that are being done on a computer have to be able to take advantage of them cores. Now, on to scenario C, the dream combo. Here, we're looking at a processor with lots of cores, high clock speed, and a large cache. It's the dream team, the complete package, the kind of CPU you find in high-end PCs and professional workstations. So why is this combination so powerful? Let's break it down. First, many cores. This means the CPU can run lots of threads at the same time. Perfect for multitasking, video editing, rendering, simulations, and many modern software designed to use parallel processing. Second, we've got high clock speed. This gives each core the ability to complete more instructions per second. Even if a task can only use a single core, like a main game thread or certain everyday applications, that one core is super fast. And lastly, we've got a large cache. This is the CPU's ultra-fast mini memory. A bigger cache means more CPU, means that the CPU, can spend less time waiting for the data from RAM. Instructions and data can be accessed much more quickly, so everything follows smoothly. When all three characteristics are strong at the same time, the CPU becomes extremely efficient. It can blast through single-threaded tasks, handle multiple threaded workloads with ease, and keep data close at hand so it's always ready to work. This is why high-end PCs often cost a lot more. You're paying for high performance in every area, not just one of them. So to summarise, a CPU with many cores, a high clock speed and a large cache delivers top-tier performance across almost all types of workloads. It handles multitasking, gaming, creative work and heavy processing all at the same time without slowing down. It's the ideal setup when you want maximum speed, maximum efficiency and maximum power. Right, on to some general information about exam tips then. So remember, be ready to explain these characteristics, not just state them. Compare characteristics individually and in combination if you need to, and make sure that you're using those key terms. So parallel processing when it comes to cores, fetch, decode, execute cycle, instructions per second, and bottlenecking. So typical 2 to 4 mark questions are going to require you to link the change in these characteristics to the performance. And again, going back to those key terms, make sure you talk about cache size, not just cache. Make sure you talk about number of cores, not just cores. Make sure you talk about clock speed, not just speed. When it comes to bottlenecking, so bottlenecking is about a characteristic slowing the others down. So if we look at this example here, we've got a CPU which has a high clock speed, many cores, but a small cache. So the cache becomes the bottleneck. So because cache feeds the CPU with the instructions and data that it needs, if the cache is too small, the CPU has to fetch data from RAM more often, which is a lot slower. So even fast cores spend time waiting, meaning the overall performance drops despite the CPU being powerful. The cache can't keep up, so it slows the rest of the CPU down. So remember, clock speed is speed per core. The number of cores is multitasking and parallel processing. The cache size is fast access to data. Optimal CPUs balance all three of those characteristics, and changing these characteristics will affect the performance independently and together. And that's it. So thanks for watching this breakdown on the factors that affect the CPU performance. Understanding these key characteristics is going to help you in your computer science course, specifically in systems architecture questions. Now we will be releasing some short form videos, some shorts on YouTube and on TikTok looking at common exam questions targeted in this area of the specification. So if you found this helpful, make sure to check out the next video in the series and don't forget to like and subscribe and share, and I'll see you in the next one. Bye for now.